I hope you've seen the assignment number 5 is up. It's your second to last assignment. Let me share the screen. And you can see it's due as usual in 2 weeks. I'm going to get to your question, Yekta. So you can see it here. The main reason I'm mentioning it is that what you have to, one of the things you have to do in an assignment, the first thing you have to do is code a function. So basically assignment is worth 100 points. But the first thing you have to do is create this function, create network, that is worth 35 of those 100 points. So it's worth the most points. But not only that, basically without this create, can you mute yourself unless you're asking a question, please? So you basically, in order to do anything else, you cannot do it without this create network. So basically everything else you do in the assignment requires what this function creates. So you won't be able to do other parts without doing it. And this is the hardest part in this assignment and kind of elaborate, and you have to understand what you need to do. Yeah, I mean, it's all doable. All I want to say is start now and start with this function. Okay, this function is critical to solve. Without it, you won't be able to solve anything. Okay, so that's my suggestion for that. In terms of the grades that you've got, so for the grading, let me just mention that most of you got by now grades of assignment of test 2. If you didn't, don't worry. You should get it either today or tomorrow or Wednesday. You should get your grade for test 2. But that comes on as the price of getting the test 2 quickly is that assignment number 4 hasn't started grading because TAs are busy doing your test 2. And I put priority on test 2 because it's worth 15% of your grades, of your final grade. Okay, so when they finish grading test 2, let's say on Wednesday, they're going to slowly start grading your assignment 4. But in either case, the goal is that you get a grade of assignment 4 before you submit assignment 5. So you get feedback on the assignment before the next one is due. Okay, so let's start with the lecture. So what we're going to do today is we're going to continue with lists and algorithms and solving problems on lists. In particular 2D lists, but we have already seen them in a lecture before when we did quiz, and even in the first lecture when we were learning about the list, because these two so-called 2D lists, they appear so naturally in Python. And the reason is that in Python, the elements of a list can be anything, including other lists. There's nothing special you have to do. So in other programming languages, that's not the case. You actually have a different syntax if you want to create a 2D list, right? So what is a 2D list? It's a list whose elements are other lists. Okay, so but today we're going to revisit that and solve some problems, even though in Python, as I've said, we already seen it and it's much more natural. We're going to revisit it because it's a natural way to represent a very important mathematical structure, in particular matrices. Okay, so let's see. Let me show you a few slides. And you, probably all of you, maybe not all of you, but good fraction of you is taking linear algebra, which is kind of all about matrices, right? So here's how you represent a matrix in programming languages, in our case in Python in particular. So one way to see a 1D list, 1D like one-dimensional list, a plain old list with numbers as elements, you can think of it as representing a 1D table, as representing a row in a matrix. Or in other words, you can say, okay, this is a matrix, 1 by n matrix. So you can say that a 1D list can be used to represent a 1 times n matrix. In this case, 1 times 4 matrix. Or in other words, you can think of a list, a 1D list representing one row of a matrix. So if you have a bigger matrix, like this one here, then the first row you can represent with a 1D list like this. Second row, you represent in Python like this. Third rows, you represent like this. So we have these 3 lists representing 3 rows of this matrix. And you cap this off in Python by putting square brackets around this. And that creates a 2D list that represents this matrix. So this 2D list, so this list, in other words, so this is how you can create it. Let me just see if I can change this. All right, so just a moment. Okay, so this 2D list, has 3 elements, 1, 2, 3, and each of these elements is another list. Okay, so for example, in Python shell, you can create it like that. Then you have a variable LST that refers to that 2D list. And you have seen that the first element, so LST of 0 is this first list. Basically, LST of 0 represents the first row of the matrix. LST of 1 represents the second row. Of LST of 2 represents third row. So you can verify that in Python. So if you do LST, you get the full 2D list. LST of 0, so the first element gives you the first sublist, if you like, and that represents the first row. LST of 1 represents the second row. LST of 2 is the third row. So each of these, always think of LST of 0, that is just the variable name. So the name of this list is LST of 0. The name of this list is LST of 1. The name of this list here is LST of 2. So how do we access individual elements of the list? So if I wanted to access this number 7 here, since this name of this list or variable name of this list is LST of 0, well, I use a variable name, okay? It's LST of 0, and I want a third element, so I have to use index 2. So LST 0, 2 is going to give me this element. So let's see some examples from these slides. These are the slides from your book. Okay, so LST of 0 is the first row, and then you use 0 to access the first element in the first row. LST of 1 is the name of the second row, and you can use index 2 to access the third element in that row. And here, for example, LST of 2 gives you the last row, and you use 0 index to access the first element of that row. So that's basically all I had to show you that I have on the slides. In general, what I'm going to do today, I want to solve a problem on 2D lists. In first case, involving matricing. In second, not even involving matrices. But one of the first things that you want to know about, let's say, 2D list is how do you populate the list? In other words, how do you put elements in the list and how do you print a matrix and so on. I'm not going to be showing you that code because we really have seen 2D lists already. But in your textbook, you have that. I'll just show you the code and go through it. We're not going to code it during the class. So let me show you what I mean by that. Some most elementary things, like let's look at 2D list intro. Okay, so let's see what we have there. So first thing, how do you create a 2D list? And let's say, how do you create a 2D list that represents a matrix? Let's say I want to create a matrix 10 by 10 matrix, all filled with zeros. So the code here actually shows you that. You start with an empty list. There's many ways to do it, but you can start with an empty list. Then I repeat this code 10 times. Every time I enter, I create a list. This thing here creates a list with 10 ones, okay? And then I add that sublist to my matrix M, okay? And I do that 10 times. And let's say what happens when we print M. Okay, so it looks like we managed to create a 2D list that represents a matrix, 10 by 10 matrix, all filled with ones. Okay, but if you want to print a matrix, you typically don't want these square brackets around. The way to present matrix that you're used to is, it's like this one here that looks like, it looks like a square. So for example, here are two ways to solve this problem. In fact, they are the same. It's just that one uses looping over the elements of the list, and the other one, the second one here, looping over the positions in the list. So let's see what happens and how you code it. So this is the first one, the one that loops over the elements of the list. And this is the same solution, but we are looping over the indices in the list. Okay, so after creating 10 by 10 matrix, we print it in kind of matrixy way. Okay, so the first solution, so the outside loop is taking items from the 2D list M. So each time we take an item, these items in list M or elements of list M are 1D lists filled with 10 elements, all filled with zeros. So then you go through them and print elements of that row. So basically, item is a row, and then you go through the row. So the item is a row, you go through the row and print elements one by one. Notice that when you print an element of a row, you don't want to actually go to the new line. So when you see here, after printing the first zero in a row, you don't want to go to the new line. So you should change the default behavior of print function by saying, don't go to the new line, instead make a space. But once you finish printing a row, so that's what this does, it prints one row. Then when you finish, then you do one of these print things just so you go to the next row to print it. Okay, so all of these kind of elementary things, you have them in your textbook if you want to view this more. And also I will post this code on Brightspace. But let's now solve something for this class. So something that has to do with matrices. Okay, so let's do new file. So what I want to do is I want to design a function that, given a matrix or given a 2D list that represents a matrix, that returns true if the matrix is diagonal matrix, and returns false if the matrix is a diagonal matrix. Okay. So we want to write a function is diagonal. So you give me input is a matrix. So a 2D list, the list of numbers, of ints, let's say, and I want to return a Boolean. So true or false, true if the matrix is diagonal matrix, and false, false otherwise. Okay, so to do this, we have to first know what a diagonal matrix is. So you are taking, those of you who are taking linear algebra, does anybody know what is a diagonal matrix? Anyone?
Where all the numbers in the diagonal are zeros, or the opposite?
It's the opposite. Yes, it's the opposite. Okay, so the matrix is diagonal. Let's put it here as a reminder for ourselves. M is diagonal if and only if you like, all the elements off of diagonal. Off, is that how you spell it? Off of diagonal? Okay, let's say all the elements not on the diagonal are zero. Okay, so the condition is that you need to check all the elements except those on diagonal. There is no condition on diagonal. You can have anything on diagonal. There can be zeros on diagonal too, but there is no condition on diagonal. The condition is that in a matrix, all the elements that are not on diagonal, that are off of diagonal, they have to be zero. If that condition is met, then the matrix is so-called diagonal matrix. Most often, diagonal matrix that you encounter that is useful in these matrix applications is the one where on the diagonal you have all ones and off of diagonal is all zero. But actual definition of diagonal matrix, it only puts a condition of what is off of diagonal. So the elements that are off of diagonal, they have to be 0. Okay, so if they're all 0, then you return true. It's a diagonal matrix. If you find something non-zero off of diagonal, then you return false. By the way, this reminds me, since I used the word application, most of you are taking linear algebra. It may sound abstract. It may sound like most useless things there is, but actually it has a tremendous numbers of application. In fact, you are using it every day, applications of linear algebra. For example, all of you are doing Google search probably multiple times a day. The way Google started is actually by 2 Stanford students. I think it was 2000, or I should check. Around 2000, they were PhD students in Stanford University, and they wrote an algorithm called PageRank that actually algorithm determines when you do a search, keyword search, what web pages they would recommend. Okay, and that is, and you can think of internet, or in fact, all the web pages that exist in the world, you can think of them as one ginormous matrix. So what's in that matrix? In the rows, you have all the web pages. In the column, you have all the web pages. So all the web pages are both in the rows and the column. And then if you have a web page that refers to another web page, in their intersection, the matrix, you put a 1. And if this web page does not refer to that one, you put a 0. So of course, the idea is that somehow the rows that have many ones are more important because many of the web pages refer to that one. That is just where the model comes from. Anyways, so their recommendation algorithm, the one determines what they should recommend, actually does all sorts of matrix. If you like linear algebra, they use eigenvalues, they use also probabilities. So all of these things that you may think don't have many uses, in fact, have tremendous amount of uses. You can Google it, PageRank algorithm. This explains, you see some probability, you see work with matrices and so on, and you can read about the algorithm and the history of it. Another thing that is full of linear algebra and matrices is actually graphics. It's a topic that is typically very popular with the students. Many students want jobs in graphics because they have applications in gaming, in movie industry, and so on. And the graphics, it's all about matrices, because the way you can think of it, that the way image is represented is just, again, it's another big matrix. Because on your screen, for example, what you're looking at is a matrix with, I don't know, matrix of pixels, basically. Let's say you have 1,000 rows and 2,000 columns, and each one of them is a pixel, and you can represent it as a matrix where in that particular position representing a pixel, you have a color that is represented on the screen. So each image is one matrix, and when you're doing graphics, basically you're manipulating matrices, okay? But that part of kind of these applications, it's outside of the scope of this class. But those who want to learn more, you should look at this book called Coding the Matrix, Linear Algebra Through Computer Science Applications, or rather in a course. The book is written by one of the top researchers in computer science, a professor at Brown University. And it's actually has, and I know the assignments used to be in Python, so you can learn about these applications in linear algebra and then code them in Python if you're interested to learn more. Okay, so that's on the side. So let's go back to what we were trying to code, which was that we were trying to determine, write a code that determines if a given matrix is diagonal matrix. Okay, so first thing first, let's first agree that we all understand the definition, what we're looking for. So when is a matrix a diagonal matrix? It's somehow implicitly in a definition of diagonal matrix, we are assuming we are working with a square matrix. So what's a square matrix? It's a matrix that has same number of rows and columns, like that 10 by 10 a matrix that I was showing you in the previous code, right? So it has to be a square matrix, because otherwise even the word diagonal is not even well defined. If you're looking at 3 by 10 matrix, what's a diagonal, right? Especially saying the diagonal, really. In 3 by 10 matrix, either you can say there is no diagonal really, or you can say there are many diagonals, right? Going through the matrix, okay? So implicitly, in fact, we are assuming that the matrix is a square matrix, that the number of rows and number of columns is the same. So in fact, a matrix is a diagonal matrix if you meet two conditions. One, M is a square matrix. M is a square matrix, meaning number of rows and number of columns is the same. And two, all the elements not on the diagonal are 0, okay? And let's agree, when we're talking about diagonal, even in a square matrix, you have two diagonals, this one and that one, right? And we're talking about this one, right? 0, 0, elements position 0, 0, 1, 1, and so on. That's our diagonal. Okay, so let's now code this. So there are actually two conditions. One is that M is a square matrix, the other that all the elements of a diagonal are 0. So first, let's check the matrix is a square matrix, okay? So what do we have to do? I have to go and take every row and see, does it have the correct number of elements? In other words, does this row have the same number of elements as the number of rows in this whole matrix, right? If I take an individual row, well, the number of elements in that individual row is actually a number of columns. So I have to check that each row has a correct number of elements. Okay, so let's take rows one by one. So here's how you do it. We can loop by the position. So for I in range len of M, let's see what we have to do. Okay, let's first understand what is M of I. Okay, so when I enter the loop, so this, when this is 0, what is M of 0? If I have a 2D list, then M of 0 is list itself. So M of 0 is going to be the first row, M of 1 is going to be the second row, and so on. So M of I, when I enter the loop, M of I is just a row. In fact, you can, to simplify the coding, you can even do this. You just rename it. You say row is equal M of I. And now you work with the row, knowing that the row is actually 1D list. You can simplify coding like that, but just let's stick to the typical matrix variables, let's call them. So M of I is a row, a current row that we enter the loop with. Okay, so what I have to test is I need to see, is the number of elements in a row correct, right? Is the number of elements in the row M of I, is it equal to the number of rows of the matrix? So what should I put here? Anyone?
If len of M of I is equal to len of M.
Right, exactly. So this is the number of rows in a matrix, and I need to make sure that each row has that many elements, right? That's what I want. But usually when you're testing something, you better test what you don't want, because then you can stop. If you find something that is not what you want, you might as well just stop. So we are asking if the number of elements in a row M of I is not equal to the number of rows in the matrix, then I might as well immediately stop, because I learned that the matrix is not even square matrix, let alone diagonal matrix, and I can return false. Okay, so this part here, this loop takes row or M one by one, so it takes row M of 0, M of 1, and for each of them tests that each row has correct number of elements. So if we ever get out of this loop without returning false, over here, if you ever make it here, we actually know that M is a square matrix. If we here, let's say here, okay? All right. Are we done? Should I do return True?
No.
No.
Okay, no. All we know is that the matrix is a square matrix, but we didn't test the second condition. So we only make sure the first condition is true. Now we have to test the second condition. Okay, I can hear somebody, so please mute yourself. Whoever is having some noise home, which is understandable, but don't forget to mute yourself. Okay, so now we have to test. Next we test if all, so we do two now, right? We are first testing one, and now we're going to test two. We know the matrix is a square matrix, and I want to test now this. Are all the elements not on the diagonal, are they all zero? So this tells you how do we solve this. So this tells me I should pretty much go through the whole matrix, element by element, one by one, and test if they are equal to zero, but kind of ignoring the elements on the diagonal. So I look at all the elements in the matrix, test I use zero, I use zero, I use zero. If I ever find something that is non-zero, but off of diagonal, I return false. Otherwise, when I come to the end, I return true. Okay, so the solution tells us I should be looking at individual elements of the matrix. So in the previous part, all I needed is rows, not individual elements. Okay, so now first I have to take a row, and then once I have a row, I have to go through the row to get the individual elements of the row. So let's repeat this. So this way I get a row. So I copy this part. I can copy this to get a row. So we now know again that M of I, when I come here, M of I is a row. Okay, so now that I have a row, I need to go through the individual elements of the row and check are all the elements equal to zero, at least those that are off of diagonal. Okay, so I need to go through all the elements of a row. So row may have lots of elements, so I need a loop to go through the elements of a row. So I do for j in range len of how many elements a row has. It has m of I, len of m of I elements. Although we checked already, we know that they all have len of m. So I could also put len of m because they all have the same number of elements. Okay, so once I'm here inside of this, the second loop, I'm looking at m of I, remember, is my row. So that's the name of a variable. M of I is the name of a row, and row is a 1D list. So this is just the name of the 1D list. Okay, and this index j, it goes from 0 to the last, it produces indices from the 0 to the last position in the row. So if this is the row, if M of I is the name of your 1D list, then with j, I can access a current element in that row. Okay, so M of ij is simply an element in row I in position j. Okay, an index I in position in index j. Okay, so this is an individual element of the matrix. And I want to test, so what am I looking for? If you're not equal to 0, then I should, so I'm looking, the elements off of diagonal should be 0. So if you're not 0, then I do return false. Okay, is this correct?
No, you have to add another condition, and if I and j are not equal to.
Exactly. So this here, indeed, it would be correct if I knew that this element of a matrix I'm looking at, if I knew it's not on the diagonal. So I have to say, if I find a 0 and that element is not on diagonal, so what I'm doing here, and we were told actually the Boolean expression, but what I did in previous class because was to say, I am looking for something that is not 0. What's an outlier? What is the thing that I don't want? That I found a 0 and this element M of I, j is not on the diagonal. So we need to find the expression that test is the element on the diagonal. Okay, so how do we do that? We were in fact told, but let's explain it. What are the elements that are on the diagonal? So those are the elements in position 0, 0. So M of 0, 0, M of 1, 1, M of 2, 2, M of 3, 3. These are the elements that are on diagonal in the square matrix. So when you have that I is equal to J, then you are on the diagonal, okay? So here, when you are having these two are the same, and I and J are the same, then you are on the diagonal. When they're not the same, then you are not on the diagonal. So what is it that breaks the rule 2 is when you find an element that is not equal to 0 and they are not on the diagonal. In other words, I is not equal to J. When both of those conditions are met, it means you found an element off of diagonal that is not 0. You might as well stop and return false. Okay, if you go through all of these elements, both of these, if you go through all of this, so this whole code is going through all the elements of the matrix and checks for the outlier. If you never found it, so if you never find a non-zero element off of diagonal and you went through all of them, which is what these two loops do, then you can safely conclude that you meet condition 2, and because in fact here, if you make it here, you're meeting both condition 1, your square matrix, and you don't have a non-zero for diagonal, you might as well return true. So that is how you solve this problem. Are there any questions about this? Okay. In that case, let's move to the second problem.
I have a
Go
question.
ahead.
Okay, so the last part, I didn't get why you put I does not equal to J.
Because when I and J are equal, so what situation would be, let's say we just started. So I is 0. Okay, so this loop starts here. I starts at 0 because first thing range produces is 0. Then we come here, the first thing this range produces is 0. So I and J are both 0. Okay, so what we are testing here is M of 0, 0 is this element. What we end up testing first time we come is M of 0, 0 different from 0? Let's say M of 0, 0 is 1. Can I conclude, should I return false? Can I conclude that the matrix is not diagonal matrix? Does it fail condition 2? It doesn't.
It doesn't.
It doesn't because element M of 0, 0 is actually on diagonal and it can be anything, okay? So what we are looking for is element like that, right? The one that is not equal to 0. So we find the 1, but we want to make sure that it's not on diagonal. So when you're testing I, for example, if I is 1 and J is 2, M of 1, 2, when 1 is not equal to 2, M1, 2, that element is not on the diagonal, okay? So 1, 0, 0, 1, 1, 2, 2, and so on are on the diagonal. So here you're making sure that the element is non-zero and that you are not on diagonal. If you find such a thing, you are not a diagonal matrix.
All right, thank you.
Matt?
Yeah, sorry if I've already answered this, like you probably have, but does the only left to bottom right diagonal, is that the only diagonal that matters for a matrix? Like your top right to bottom left diagonal?
Yes, yeah, in a square matrix, this is typically, that's a definition. This is what is considered the diagonal, the 1, 0, 0, 1, 1, yeah, from top left to bottom right, yeah.
So the other diagonal doesn't matter in terms of
Not in this definition, not in the definition of diagonal matrix.
Okay, thank you.
No problem. Okay, so that's it for that problem. The next problem we're gonna solve, it's so-called frequency counting, and I'm gonna show you on. First of all, I'm gonna use my tablet to explain what I actually would like, what we would like to solve. Okay, so let me go to my, all right, so here it is. So we had, world had, but in much more specifically, United States had election, as you all know, I'm sure, last week. And so imagine that all the results of the elections, every time you vote, you put down somebody's name, the name goes into the list. Okay, so you have a list of strings, which are names of the candidates. Okay, so, and so what do we have in that list? Each time a person votes, whatever names they voted for, it goes in the list. Okay, so let's say the votes are Biden, hopefully again Biden, then we have Trump. Actually, there were no, in a previous lecture, I was just thinking, okay, yeah, in US, it's kind of a boring example because in US, they only have 2 candidates. But then I realized I was wrong because first of all, I remember that Kanye West actually was officially a candidate. He even received about 50,000 votes, you know, so maybe the next thing was Kanye West. But between these 2 classes, I actually Googled it and there was a certain number of candidates in US election. So there is even a person who got close to 2 million votes, right? So I'm just going to put a Joe for that person and so on. So certainly it's not the case that there were only 2 candidates, right? So let's go back to my example and figure out what is it that I want solved. Okay, where did it go? Here. Okay, so we go through the list and we have, let's say, Trump again, Biden again. Okay, hopefully you get an idea. So this is a list of strings, okay? And in case of US election, about 150 million people voted. So we would end up with a list containing 150 names. So what do you want from election? You want to know how many times each name appears. Each unique name, how many times does it appear? Or rather, each distinct name, how many times does it appear? That's how you determine the results of elections. Okay. In other words, what you want to know what is the frequency in this list. That's why this problem is called frequency counting. You want for each distinct element, you want to count how many times does it appear in the list. Okay. So if this is a 1D list of strings containing the votes in US presidential election, what we want at the end, after processing, I want a function, I want to design a function called frequency counting, but given a list like this, produces a frequency counts for each individual, each distinct element. In other words, what are distinct elements? We have Biden. I want something like this. String Biden, or in other words, word Biden appears, whatever, 75 million times. I'm going to round these numbers, okay, in this list. Word Trump appears 71 million times. So let's go back here. So what do we have? We have that Trump appears 71 million times. Then we have this Joe person. She appeared, let's say she had roughly 2 million votes. Then we have Kanye West. I think he had about 50,000 votes and so on. Okay, if there were other people. So what I want to produce for each distinct element, so for different elements, for each distinct element, I want to produce how many times it appears in the list. Okay, so the result, what you have to produce, somebody gave you, let you handle, your software has to handle results of presidential election. You produce something like this. Based on this, we can determine who won the election. Well, not necessarily in US because they have these electoral colleges or regions that determine who wins, but at least let's say who won popular vote In some countries, actually, they use popular vote to determine some of the positions, and some they even use a mix. All right, so this is your goal. You're given this. So let's say you're given a list, I will call it A. You're given a list A, your function has to produce something like that. Okay, so far in the class, you were basically always, I would tell you in what format I want output, in what format I want data, okay? But typically as a programmer, you don't only, your customer or whoever you're making software for, they will tell you in words, in English, of what they want. But you programmer not only determine how you solve it, but before you even determine how you solve it, you determine how you're going to store the data. Okay, so far I was the one always telling you, your input is a list, your output is blah. Okay, so in this case, right, I'm still telling you your input is a list because somehow this was produced and given to you and you are told process this. So input is a list of strings. And what I want is that for each unique string or for each distinct string in that list, I want that you give me how many times it appears in the list. That's your goal. Okay, so I want this, the thing that I circled pink. You get to decide how you're going to return this data. It's a function. I want you to return to me this data. How would you represent this data? There are various ways to do it, by the way. Okay, so how would you represent this result? What would you have your function return? What, if you were designing this function, what would you return? But I want all of this there, but how would you return that data? What would you return?
You could make a list that contains elements that have a list that contain a name and the number of votes for that candidate.
You could make a table.
That's a suggestion one. What is suggestion two?
Make a table, like the name and the number of votes.
Matrix.
Okay, make a table. All right. Name and count. Anything else?
We can do a matrix like the one before.
Right, but this is a matrix. In fact, all three of these solutions are the same, right? This is a n by 2 matrix. This is n by 2 matrix, which in Python you represent as a list containing n little lists with 2 elements, which was the first suggestion, right? So this is kind of conceptual suggestion, if you like, kind of more mathematical, and this is how you represent in Python a 2D list. And this is actually the most natural way to represent it. I'm just asking if somebody has seen some other ways to do this.
A hash map?
Sorry?
Hash map?
Oh yes, but we're gonna get to that. That's not what, that's the best way to do it. Basically use a dictionary, but we haven't got there yet. So let me show you what I had in mind. Not in mind, what you said, we're gonna code that because this is really the most natural way to do this. So let's first understand what was suggested. It's basically that you return a 2D list, okay, where the elements of the list will be little lists, and we have seen something similar in the previous class. What I want is going to be Biden, and then it's going to be a little list with 2 elements. The first is the name of the candidate, and second one, how many votes they have. So 70 is going to be an int. So we have a string, and we have an int. 75 million, right? So that's going to be the first element of the list. The second element of the list is going to be Trump. Okay, it's going to be another list with 2 elements, which is the name of the candidate and how many votes they have, right? And so on. So basically, that's a natural way to represent the number of times distinct strings or distinct names appear in the list. Okay, so let's code that. So that, let's code that solution. Okay. All right, so what is this? Yes, let's go and do new file. So what do I want? I want a function called frequency. How did I call it in my notes? I want to use the same names in both classes. Oh, it looks like only call is frequency. Okay. And I'm given a list A. In our example, that was a list of candidate names. And what we want is, this is a list of strings, for example. In general, it can be a list of objects. It doesn't have to be strings. You can do the same thing with other type of things. But in our example, it was a list of strings. And we want to return a 2D list. And I don't want to describe it here, but basically representing a frequency. It doesn't really go here, this, but we've decided what we wanted there. Okay, so for now, we're going to code this, but let me leave it there for now, empty, non-finished. Let's again, make sure we understand what exactly we want to return on an example and make a call on that example. Instead of having a list of names, I'm not going to actually use a list of names in my code. I would like to avoid typing some of these names. And instead, I'm going to use list of cities. So let's say somebody gives me a list of cities that they visited in the last 24 months, and they want to see the frequency count. Okay, so in the main, I have this list of cities. And so let's see, what do I have? The person visited in this order, this city, then I don't know, Paris, then Mostar again, then Melbourne, then Budapest, then I don't know, Melbourne again, then Melbourne again. Okay, so this is a list of cities. And after I call my function, so if I call my function here, where is my cursor? Right there. So if I call my function and pass it these cities, and I print what it returns, what I want to get, as we agreed, is I want to get a 2D list that is going to say, okay, Mostar appears in the list 2 times. Then Sarajevo, so for each distinct element, I want to know how many times it appears. Sarajevo appears only once. Then we have Paris, appears only once. So there we have a little list of 2 elements telling us that. Then we have Melbourne, appears 3 times. And finally, Budapest appears. Budapest appears 3 times. No, sorry, 1 time. Okay, so that's what we want printed. That's what we want our function to return. By the way, I didn't tell you what is the other. So if you go back to here, I was saying so this is what we concluded is a natural way to represent it. But if we were doing this several years ago, we were still doing Java. If we were doing this in Java, we couldn't actually do this with the 2D lists because of the way they limit what are the elements because of the elements of the list have to all be exactly of the same type. We couldn't actually do this. So you could only do something like this once you get the objects. So a typical workaround for that is to use so-called parallel lists, and you can actually see in them that type of use of two lists that contain related data. So another way to solve this would be to say, okay, I'm going to have 2 lists. This first one is going to be candidates. So I'm going to have a list of unique candidates, Biden, Trump, Kanye West and Joe. That's going to be list one containing all the candidates once. And then I'm going to have counts, another list. These are called parallel lists because their data is related. I'm going to have counts where if here in position, in index 0, I have Biden, in index 0 of counts list, I'm going to have how many times Biden was found in the given list, which in our case is 75 million. So in position 1 is a string Trump, it's a candidate Trump. So in the position 1 of the counts, I'm going to have the number of times that name appear on the list and so on. Okay, so we're gonna have, you would have two lists whose data is related. That's why they call parallel lists, right? In both of the lists, the data in position, in index 0, both lists is related. In index position 1 is related and so on. So you've seen this in your previous assignment. And this is a very typical way to store data in other programming languages. If you're not using objects, if you're just working with a list, then you actually encounter an additional problem. Then in other programming languages, you cannot return two things. You cannot return both of those lists, so you have to deal with that. But again, this type of solution, I think, is a little bit less natural, and its common use comes from limitations of other programming languages. Okay, so lists in Python are more powerful than list or that is array in other languages. Okay, let's go back to our code and let's code the solution I had in mind. Oh, by the way, before I do that, let's say that I want to solve a problem. So let's say somebody solved this for you. So it's now solved and you can use it. And then I said, okay, next thing I want you to solve is a function called number of distinct elements. So given a list L, so let's say this list again has many strings. Many are the same, others are not. I want to know how many distinct strings is there in this list. Okay, so in terms of in this example, it should return what are the distinct strings. Most are Sarajevo, Melbourne, Budapest, and Paris. There are 5 distinct strings. All of this list has 1, 2, 3, 4, 5, 6, 7, 8 elements. 8 strings, only 5 of them are distinct strings, so different from each other. So in that case, I would want to, if we call number of distinct on cities, I would want to get 5. If we called it on the number of, on the American presidential election, I would like to get a number, I don't know, 7, if there were actually 7 different names in that, in that list of votes, okay? So if somebody coded this for me already, how would you solve this problem? The one that given a list of L, let's say a list of string, returns number of distinct strings in the list. So number of different strings in the list. Okay, Yara, go ahead. No, somebody else?
You
Yeah,
should.
You can create.
Yeah, I think Yara was about to speak. I thought she was not going to speak. Go ahead, Yara.
Oh,
Sorry.
you should call like the first function, which is the frequency.
Okay, we call it on L, and now what?
We should count each element, I guess.
So what you want actually is how many elements does this list have? So this returns that list. Well, the number of elements in this list tells you exactly how many distinct elements you have. So it's 1, 2, 3, 4, 5. Okay, so you're returning the length of the list that frequency of L returns. Okay, so that tells us how many distinct elements there are. What about if I want to know, given a list of strings, are all of them unique? In other words, I want to return true if there are no 2 elements that are the same. If there are no duplicates, meaning every element in the list is unique. It doesn't appear more than once. So how do we do that? So I want true. Oh, go ahead, Otman.
You can make an empty list, and for every element in L, you append it to the list if it's not in that list. And if you run into something that it's in the list, you just return false.
Right. Okay, that's true. But that is like completely solving it from the scratch. Or stretch, not scratch, stretch. I don't know, whatever is the correct word for to say that. But somebody already coded this frequency thing for us. Can we use it to, you know, solve this quickly? My or my head.
So we can iterate over frequency, and for every element that is equal to 1, we know that it's unique.
Right. So if we go through this whole list and everything, every city appears exactly once, you return true. Okay. But can we do something even simpler, that we don't need to iterate through this list? So we are saying we call frequency L. Frequency L is going to return us this list, and the suggestion when you go through this list, make sure everybody appears once and everybody is unique. Is there other way to do it? Chai?
We can iterate over the items of the list and use the built-in function count.
Yes,
And
we
if
already
the count
heard.
is
Yes,
like more than
yes,
one.
that's correct. That's right. That's correct. And we already heard similar solution. Yes, that is correct. But I really want, let's say, one line solution that uses frequency. Maid, is this
Yeah,
hand?
so we can go frequency index 1 equals 1.
Frequency.
So in one line, return frequency L index 1.
No. Okay. So let me show you how. You're asking how many elements does this frequency list have? Okay. Is that the same as the number of elements in L? If it's the same, that means that every single one appears once, because if even one of them appears 2 times, the number of elements in this frequency list will be less than the number of elements in the original list. Okay, so you can just return this. Okay, so let's see.
But Professor?
Yes?
That way we don't know which element
We
is
don't
unique.
know. No. All of them are unique. I want to know that they're all distinct. Okay,
I thought
sorry
we
if I
wanted
didn't.
to know which one.
Yes, I know that all of them are that no 2 are the same. So all of that's what it said. Like all the elements are unique in the list. No 2 are the same. It's like opposite of duplicates. It's not opposite. It's the same. With duplicates, I wanted to return true. When you have duplicates here, I want to return true when there is no duplicate. So every element appears exactly once.
You forgot and equals to.
Yeah, yes. Here equal. You're right. Okay, so that's one solution. So let's finally code this actually. What I wanted to demonstrate, this is super versatile problem. This is one of those fundamental, frequency count is one of those fundamental computer science problems that appears everywhere, that you can use it to solve many other problems and so on. Okay, so let's code this. So what do we want to do? I want to go through this list A. A is our list here. I need to go through that list one by one. I take a string. So what do I need to do? I take a string from that list. I need to create a frequency list. Okay, in the beginning, the frequency list is empty, right? So we can already do that. We didn't before I put anything. Then I have to go through this given list of A. That's a list of cities. Okay. I take a string from that list. Let's say first string. And or let's say we are building this frequency list so far one by one, and I take a next string. All right, so I first of all, let's say it's Mostar. Let's say we are here, 1, 2, 3, 4th position. Let's say we are in this position. I just took in processing A, I just took next one, and it's Mostar. I need to go through a frequency list to see, is Mostar already there? Is it one of the, did I already put it in F? So I'm building this frequency list, this one. If I find Mostar in the frequency list, all I have to do is increase the count. Let's say it was 2, I need to increase it to 3 when I find it. Or If I don't find it in the frequency list, I need to add Mostar, 1 to the frequency list, right? So if it's not there, I have to add for each city that I don't find in the frequency list, I have to add that new city and say that it's here, that I found it once so far. Okay, so let's code that. So I have to go through elements of sorry. Somebody, can you mute yourself, please? So for I in range len of A, okay, I'm going through the elements of list A. And so that means when I enter here, A of I is a city, right? So when I is 0, then A of 0 is Mostar. When I is 1, we are looking at Sarajevo. I is 2 is Paris, so that I misspelled it. All right, and so on. I of 3 is Mostar again, and so on. So A of I is a city. I'm holding in my hand a city. So now, what did we say? Now that I have this city, the next city I took, I have to go through the list F to see, is the city already there? Because it's already there, I just have to increase the counter. So I have to go through F, my frequency list. So let me now have a new loop that goes through F for J in len of range len of F. Let me now, so what do I have to do? So F of J, what is F of J? This is very important to understand, and there was lots of students were confused about in previous class. What is F of J? This F is a 2D list. So individual elements, in this case, F of J is an individual element on F. So this is F of J, is a list with 2 elements. In other words, F of 0 would be this. Once we create it, this is F of 0, this is F of 1, this is F of 2, and so on. Okay, so I want to test for F, I'm going through the list, I want to test F of 0 is a list with 2 elements. I want to know if the city I'm currently looking at, A of I, is it there, okay, in the first spot? So I want to test if my city A of I, is it equal to what? I want to know, is my city already in the little list F of J? So what should I put here?
F of J of 0?
Exactly, because in position, F of J is a little list with 2 positions. In the first position, so index 0 is the name of the city. So if these 2 are the same, I know my city is already there. So all I have to do is in that F of J is the little list containing my city. I have to increase the count of in F of J list. So F of J has 2 positions. The first is the city, the second is the count. So I have to increase that count by 1. So what should I put here?
F of J 1 is equal F of J 1 plus 1.
Exactly, because the second element in that list, F of J 1, the second we found the city in position F of J 0. Therefore, in the second position of that little list is the count for that city, and I should increase it by 1. All right. So that's if we find it. So here, outside of the loop, if we went through the all of frequency list, and this was never true, we never found our city, that means that what I should do is I take this frequency list and append to it. So my city is not there. So I should add to the F frequency list, the little list with 2 elements containing the city. A of I is the city, basically containing the string, and the count. Count is 1. So far we found 1. Okay, but you should ask yourself, how do you know over here if you found the city? We weren't keeping track here if I found the city. So here, what we were doing here in these pieces of code was saying you go to the frequency list looking for the city. If you find it, increase that count by 1. But we didn't keep track if we didn't find it. I need to know that I didn't find it. I should do this. So once I'm finished with this list F, I need to test that my city A of I, if I didn't find it, only then I should add that city to the list. So I better keep track if I found something or not. So here's a typical way to keep track of something. So I'm going through F looking for a city. So before I even start going through the list looking for a city, I may assume before I start, I didn't find it, right? So I have a little variable false that's going to keep track that I find it or not. Inside of this if statement, so if this is true, that means we found a city. In that case, I change my variable to true. Okay, I indicate to myself, oops, I found it. Not only do I increase the count by 1, but this little flag, and by the way, this variable is often called flag because you use it just to flag for yourself as something. In addition to increasing, you tell yourself, okay, I'm remembering that I found this element. Okay, so once you get out of this loop, I now test if found is equal false, for example. That means I didn't change it. So this was never set to true. It means that here, I didn't find a city. So in that case, I can safely append a little list with 2 elements containing my city and count 1 to F. So once we are done going through all the cities, that's the outside loop, we can return F. So basically that is our solution. Before I get to a question, Maid, let me just see what happens in the beginning. It may look like a bit of a magic because we start with an empty list. So at the very beginning, when we do say, go through the list and take I of 0. So what's I of 0 is Mostar, because actually cities is sent to A. So not I of 0. A of 0 is Mostar. We come here, found is set to false. A of I is Mostar. We come here and it says, for J in range len of F. What's the length of F on the beginning? 0. We just created F is 0. We didn't add anything to it. So this is for J in range 0. So function range 0 is not going to produce anything. Remember that range function says start at 0, go up to 0, produce a sequence. Well, if you start to 0, want to go up to 0, there's nothing to produce. So this whole thing is skipped here. Obviously found is still false. So we add Mostar 1 to the list. First time we go through this outside for loop. Next time, it's going to be Sarajevo and so on. So that's a solution. Maid. Okay, so for the end of the class, what I'm gonna briefly go back to analysis of algorithms and ask you how many operations do certain solutions take. All right, so let's look at this one. Let's first of all figure out what does this function do. We have a range function. We have a range function here that produces numbers from 1 up to n minus 1. So this just produces number 1, 2, 3, 4 up to n, including n, and it prints them, right? So this function, if I call it with 100, is just going to print these numbers. Okay, so I want to know how many operations is this solution roughly? So what does this function do? It prints integers 1 to n inclusively, like that would be in English, right? It prints in, what does the function do? It prints integers 1 to n. You give it an n, it prints integers 1 to n. So how many operations does this function do roughly? In particular, forget even roughly, how many times is this print call, this print statement, how many times is it executed?
N times.
N times. So we have here, this is executed n time. You can think of printing one number cost you 1. The loop is executed n times. And each time you do one operation, it just produces a number. So this is 2n. So this is linear solution. Okay, so this is O of n. This is a linear solution to problem that somebody gives you, print all integers 1 to n given n. All right, what about the next one? The next one here, what does it do? This one produces number from 1 up to n with a skip of 2, okay? And then it prints each of these numbers followed by a star, okay? So this says, how many times is this print statement, let's say this one here, how many times is this print statement executed, roughly? Let's see what we get if I put 100. So we understand what this does. Print. Okay, so you see it prints odd integers from 1 to 100 separated by a star. So how many solutions does this do roughly, this printing odd numbers up to n?
Half
And
n.
divided by 2.
N divided by 2, exactly. So this line is executed n divided by 2. And then in terms of big O notation, this is done n over 2 times, this is done n over 2 times, this is done n over 2 times. Altogether, this is roughly 3 n over 2. We remove the constant. This is also linear. All right. What about this one here? It says prints something. This one there. Let me first ask you, before I ask you how many times this print statement is executed, let me just ask you. So see here in English, I wrote what the function does, not in Python. It doesn't say you go, you create I and go from 1 to n. I want English. You say this function prints odd integer, given integer n, it prints all odd integer up to n, all positive odd integer 1 to n. What does this one do? Given in positive integer n, it prints all positive integers from 1 to n, okay? So what would be your description? What does this do?
It prints from 1 to n twice.
No?
It prints a pair of numbers, so like 1, 2, 1, 3, and then 2, 1, 2, 3.
So it prints all the possible pairs of numbers all the possible pairs that you, basically combinations, all the possible pairs that you can create with numbers 1 to n. Okay, so let's actually see that. Run. I don't know what, save. Let's run that one. I say, oh, show me all the pairs of numbers that you can create with numbers, what was it, 1 to 20 inclusively. Okay, so it's gonna go now a long time, right? 1, 1, 1, 2, 120, then 2, 1, 2, 2, 2, 3, 220, 3, 1, 3, 2. Okay, so it prints all the possible pairings you can do with numbers 1 to n. Okay, so how many operations does this do? It's still printing here. So how many times is this print statement executed?
N squared.
N squared, exactly. There's basically n squared pairs. So this one is executed exactly n times. Each time you enter here, this one is executed n times. So we have n times n, that's n squared. So this line here is executed exactly n squared times. And then this one n squared and this one n squared. So that's like 3n squared. So this is quadratic solution to a problem. Oh, you need to print all the possible pairs of numbers that you can make with numbers 1 to n. Okay, so this is a quadratic solution, but here's where I was getting to. This function here that I call mystery, we start with a number n, then we enter the loop, then we half n, and we print n. Well, we start with n, we print n, then every time we enter the loop, we half n, then we print it. We test if the new n is bigger than 1. If it is, I half it, I print it. I half it, I print it. And you keep on doing this as long as n is greater than 1. Okay, so the same question. How many times is this print statement executed?
Would it be square root of n?
No, it's less than n, but much less than square root.
It's square root of n.
Yeah, so it's way less than square root of n, right? basically the number of times this print statement is executed, it's exactly the same as number of times this loop is executed. So, so we have to figure out how many times is this loop executed. Anybody?
Does it have something to do with logarithms?
Yes. So let's understand it here. Please pay attention. Logs are going to follow you everywhere in efficient algorithms and computer science. In fact, one of the famous algorithms that we're going to study next time is related to this. So let me show you this. So what do we want to determine here? No, not that, this. Okay, so let's look at both this. I'm going to be done in a minute or two, so give me a time to finish this. So let's see that, let's take it on an example. So let's say we start with n is 64. Okay, so our function is going to start, if I call mystery on 64, so 64 gets printed, right? So n is 64 and that gets printed. N is 64 is bigger than 1. And so we enter here, and then 64 divided by 2 is 32. So new n is 32. So the new n is 32. We print it. We come here, is 32 bigger than 1? It is. Then you divide 32 by 2, that's 16. New n is 16, and so on. Okay, so let's do this in general. So we start, first time we enter the loop, we have a number n. We print that number n, okay? And then n gets halved. So next time I enter the loop, the value of n is n over 2. You can think of it that your n is a power of 2, so it's divisible. To forget about the, let's say we're doing integer division. Okay, next time, so new n is n over 2 now. So second time we enter the loop, n is actually n over 2. All right, so the new n is n over 2. Okay, new n is n over 2. Next time I enter the loop, so n is now n over 2. That when I enter the loop the third time, when I enter the loop the third time, n is n over 2. Then I divide it by 2. So basically, third time I enter the loop, n is n over 2 times 2. Okay, twice divided by 2. Maybe it's easier if I write it like this. Okay. So this is first time I enter the loop. We have an n. I leave a loop, it's n over 2. Third time, fourth time I enter the loop, I divide by 2. So my n is this now. So this is my n, and I divide by 2 again. This is asking me to divide by 2. Okay, next time I enter the loop. Okay, this is my current n, and then I need to divide it by 2. So the new n is going to be this. Okay. Each time I enter the loop, I first test, is this not, before I enter the loop, I'm testing here, is it bigger than 1? Okay, is this bigger than 1? So how many times am I going to enter the loop? The number of times, so here's what you have to solve. How many times can I divide n? So this is your number, this is your x. How many times can I divide n by 2 before I get something less than equal to 1? That's the, that's the equation that you have to solve, right? So I have number of times I'm going to execute the loop is equal to the number of times I can divide 2. So this is that number of times I enter the loop. I'm going to call that x. So before I get something less than equal to 1, because once I get something less than equal to 1, then I don't enter the loop here. Okay, so what I was solving here, n is 2 to the x. X is what I want to know, right? How many times do I enter the loop before I get something less than equal to 1? Let me change the color here. Let me even better. Let me move this. We are basically done. right? So I go to the next line. I just rewrite it. N over 2 times 2 times 2 times 2 times 2 is less than or equal to 1. Well, that's this. That's this. So you rewrite this. This is n is less than or equal to the x. X is what you want to know, right? So you just take log base 2 of this whole thing, and you get that x is at least log base 2 of n. Okay, so as long as you enter, the moment x becomes at least log base 2 of n, this thing is going to be less than 1, and you're going to exit the loop. So the maximum number of times you're going to execute it, the loop is log base 2 of n. So when I ask you, if I ask you something like, how many times can you divide n by 2 before you get something less than or equal to 1? Well, that's the definition of the log. You just say that's log base 2 of n. That's what log base 2 of n is. For example, when n is 64, I'm asking you, what is log base 2 of 64? Well, that's how many times you can divide 64 by 2 before you get something less than or equal to 1. So let's check it. 64, 32, 16, 18, 16, 8, 4, 2. Okay, it's 6, right? We don't want 1. So a log base 2 of 64 is 6. Okay, so it's a very slow growing function. You can go to Python, import math, and see that log base 2 of, I don't know, million is 20, and so on, right? So if you want to know what log is, you just, log base 2 of n is the same as saying, how many times can you divide n by 2 before you get something less than or equal to 1? Or equivalently, it's like saying 2 to the what is n, right? 2 to the what is 64. Well, 2 to the 6 is 64. I hope I didn't make a mistake with 5 or 6 or something. Okay, that's all I have for today. I'm going to